Welcome to EC TechNest. This is day 10 of the Verilog and Digital Design series. Today we are talking about a very important topic, that is generating clocks and stimulus in test benches. So we'll begin with generating the clock signal. The clock is the heartbeat of your simulation. In Verilog we use a forever loop or an always block within an initial block to toggle a bit at specific frequency. See, this is a basic way how you generate a clock. You have a separate module for the clock within the test bench. You begin with initial. First you initialize the clock to be a 0, and then to toggle it, for the first 5 seconds the clock will be in the positive cycle, and after that for the next 5 nanoseconds it will be in the negative clock cycle. So you get that square wave like this. So after 200 nanoseconds the simulation will end. So this is the standard method used to calculate the half period of the clock. It is 1 by 2 times the frequency. We'll understand how this formula has come. First we have the period. This is the total time it takes for a clock signal to go from low to high and back to low again. That means we're talking about a full clock cycle. So whatever is your frequency, consider you have 100 megahertz, that is 100 into 10 power 6. So this time period is going to be 1 by 100 into 10 power 6. The half period. In a standard square wave 50% duty cycle, the clock stays high for half the time and low for half the time. So as I told in the first slide, you will have half for a positive cycle and half a negative cycle. So that is what is half period. So combining these two formulas, the half period formula and the period formula, we get the combined formula. So the formula for half period becomes 1 by 2 times the frequency. Let us see different examples. So as I told, let's simulate a 100 megahertz clock. So your frequency is 100 megahertz. Period will be 1 by f. So 1 by f is 100 into 10 power 6, we'll get 10 nanoseconds. But you know that half period is 10 nanoseconds divided by 2. You will get 5 nanoseconds. So for the clock cycle, it will toggle every 5 nanosecond, creating a 10 nanosecond 100 megahertz cycle. So the complete clock pulse is of 10 nanoseconds. So you have other examples, 50 megahertz, 100 megahertz, 250 megahertz, 1 gigahertz. So for that all you can calculate using this formula, 1 by 2 times the frequency. At that time you will get the different Verilog toggle delay. This can be used in a simulation. After this, there comes different ways of generating clock pulse. As I told in the first slide, you can use a forever loop or a always loop. Yeah, always block. The forever loop is the most recommended one, and it is commonly used in Verilog. First, we'll declare the clock as a reg. Initial begin. We'll initialize the clock to be first 0. Forever with 5 nanosecond delay. That not delay. It will toggle for every 5 nanoseconds. It means for the first 5 nanoseconds it will be a positive cycle, and for the next 5 nanoseconds you will have a negative cycle. So the complete clock pulse will be for 10 nanoseconds. The always block, here also it is the same, but instead of writing in the initial block, you will not use an initial block, you will write it outside an initial block. Same, no difference in this, just you are removing this initial block. Now comes clock dividers. So your system clock will be at a particular frequency, but for a specific device or a specific tool that you would be using within the top module, you might require a slower clock. So at that time I'll use a counter. So many of you might think, how can we slow down a clock? See, this is a practical example how they do it. You declare a 4-bit counter, and I register a variable called as clock division, and I'll initialize it to 0. So at every positive edge of the system clock, I'll begin the counter. If counter is equal to 4, you will begin it. It means until counter begins 4, we'll keep on doing it. Counter should be less than or equal to 0. Your clock division will get the negation. It means it toggles every 5 cycles. If this is not happening, you will increment the counter. This is the basic working. We'll see it with a proper example. So yeah, since it's a 4-bit counter, it will count till 0, 1, 2, 3, 4. So it will have 5 cycles, right? So in the beginning, whatever your system clock is there, it will be ticking for every 1 second, or you can take it as 1 nanosecond, it will tick. So it will tick 10 times. What we will do is, when we put a counter, what happens is, for every 5 cycles, it will start ticking. So 0, 1, 2, 3, 4, then it will tick. So when you see it in a slow clock, what will happen is, it will wait for the 5 counters, then it will go high. Again, it will wait for the 5 count, then it will go low. So this is how they slow down the clock. So also we have for a high speed applications, we require PLL, phase lock loop, or the MMCM, mixed mode clock manager. This is a bit lengthy topic to talk about, so we'll discuss it in the next lecture. After we finish off the basics, we'll talk in depth about this. For now, you can understand that it is for requirement of high speed clock requirements. Instead of designing and writing Verilog code every time like this, or writing some counters or something to increase the speed, we have something called as phase lock loops. They are dedicated hardware primitive blocks on the chip that takes an input clock and multiply or divide it to the desired frequency. Same goes with MMCM, is a critical hard IP. It means it is already a hardware primitive block in FPGA and ASICs. While you can write Verilog code to divide a clock by even a power of 2 using a counter, you cannot easily multiply a frequency or shift a phase using standard logic gates. This is where these dedicated analog digital hybrid circuits come in. Now the most important part will be a time scale. I'll tell you where this is used. When you saw our first code, I wrote here, so 1 minute. Yeah, I wrote a time scale here. So we understand how to generate a clock, but we did not discuss about this, right? So now we are going to talk about timescale. The timescale directive is a compiler hint in Verilog that tells the simulator two things: the unit of time for your delays and the precision with which the simulator should round those delays. So in the previous when we used we wrote here forward clock or always clock, right? Nobody questioned what could be this hashtag 5. Is it 5 seconds, 5 nanoseconds? How will I know it? So that is why we use time scale. So the first part of the time scale is unit. What it tells is, if we write hashtag 1, it means it is hashtag seconds or nanoseconds or milliseconds. Look at the unit to decide if that is 5 nanoseconds. If you have written 5 nanosecond, 1 ns here, so if you write 5 in your generation of clock, it will return it as 5 nanoseconds. The precision. The second value is for precision. Consider sometimes you might want, like if I write here 5.25, should I consider the 0.25 will be your question. So the second value defines the granularity of the simulation. Even the smallest possible increment of the time the simulator can track. Any delay smaller than the precision is rounded. Here one thing you have to keep in mind, the precision must always be equal to or smaller than the unit. It means the precision has to be smaller than this unit. If this is 1 nanosecond, here you can write 1 nanosecond, but you cannot go more than that, like microseconds. You cannot. You have to go either in pico. Example, see, as I told, 1 nanosecond, the precision what I am giving is picoseconds. So what my clock will do is, I have a 5.25 here. Since I have mentioned that even precision is picoseconds, even this 0.25 is considered. What it will write it as 5.250 nanoseconds. So the resulting frequency will be 95.23 megahertz. But if I am using the precision 1 nanosecond, what will happen? This 0.25 will get neglected. It means it will round it. So my resulting frequency will have an error. So precision becomes very important. We'll see the two steps here. 1 picoseconds refers to 0.001 nanoseconds. You can use decimals like hashtag 10.505 and the simulator will track it accurately to the third decimal place. This is very important to remember. It will do it till the third decimal place. Precision 1 nanosecond. If you try to write hashtag 10.5, see above, this is below zero point 0.5, right? So it rounded up to the previous value. In this case, if I had 5.5, this would be 6 nanoseconds. See, if you write 10.5, the simulator will round it out to 11. It means if it is zero point 0.5, it will increment it to the next value because it cannot see fraction of a nanosecond. Since your precision is wrong, it will not consider it only. Multiple time scales. This is a bit very important when we are handling bigger projects. Most of us tend to use different time scales. This can be a bit tricky. If you miss it, no, there are a lot of clock errors that you will get. In a large project, different files might have different time scales. The simulator typically picks the smallest precision across all compiled files to use as the global time step. However, to avoid massive headaches and race conditions where signals change in an unexpected order, it is a best practice to keep a consistent timescale across the entire project. Define it in a header file or at the top of your test bench. What it means is, as I mentioned in the first slide, you will mention it here at the top of your test bench as a header. So yeah, I came out of the slide. If you have any doubts, feel free to put it down in the comment section. Thank you.